Additivity plays a subtle role right through the theory of chance, and it is going to be manifested here in a result on additivity of expectation and variance. So let us begin again with the simplest setting of two variables. And to keep ideas clear, let's focus on a setting where we have independent chance experiments. So we consider two independent trials resulting in continuous chance variables x and y. X is governed by some probability law, a one-dimensional density, say P1, with expectation mu1 and variance sigma 1 squared. Y likewise is governed by some one-dimensional density, say P2, with expectation mu2 and variance sigma 2 squared. The underlying composite experiment here is engendered by a product space of pairs x, y, and the underlying product measure is specified as a product of the individual one-dimensional density functions. Okay, so here we have it. Now, before we launch into a characterization of expectations, it'll be wise to bear in mind the very basic change of variable theorem for expectations. So consider a transformation. Think of x and y as your coordinate variables, and a measurement, a transformation, which takes x and y into a function f of x and y. So now we have a new chance variable, f of x and y. How do we compute its expectation? Well, a simple way to go about it is to look at the values of f of xy at a given point xy, weight it according to the mass density of the pair at that point, p of xy. In this case, of course, we've assumed that p of xy factors into a product of two individual one-dimensional functions, and integrate out over all possibilities, sum in the limit over all possibilities, and Bob's your uncle, you've got an expression for the expectation. How about the variance? Well, we can do it exactly the same kind of argument. We start at a given point x, y, at the value of f of x, y. Consider its distance from the expected value, e of f of x, y. Now, that difference squared gives us a squared distance from the expectation, weighted according to the mass density of the pair. In this case, the mass density of the pair is a product of one-dimensional functions, and integrate out over all possibilities. So this is a very simple change of variable theorem. Now let's apply it to the very simple function where we have a sum. And so, suppose f of xy is x plus y. What can we now say about its expectation? Well, by the change of variable theorem, the expected value of the sum can be written as take the values x plus y, weighted according to the mass density, integrate out all possibilities for x and y, and there you have it. Now, the fact that the function we are dealing with has got such a simple additive form here has got an immediate consequence. In the integrand, we have a sum, x plus y. But integration is additive, right? Of course, this is just a manifestation of the associative property of addition, namely, to wit, that addition can be done in any order. And so, if we isolate the term x and then the term y, we can put together the contributions of each and add them up. And so we can write down this double integral as a double integral over x times a density function plus a double integral of y times the same density function. And now we've got, on the right-hand side, two double integrals, and we evaluate them naturally by iteration one integral at a time. But now we notice that the integrands are separable into functions of x times functions of y, and therefore the integrals separate as well. And so the first double integral gives rise to a product of two one-dimensional integrals. The second double integral gives rise to an analogous product of two one-dimensional integrals, and I've color-coded them for visibility. Now take a look at each of those single integrals on the right-hand side. Do you recognize them? Pause, think about it, and then proceed. Now observe that the first integral, colored in green, is just the expectation of the first chance variable, big X. The second integral, color-coded in red, is just the area under the density function P2. By normalization, that area has to be unit. The third of the integrals is the area under the density function P1. By normalization of that measure, that integral is unit. And finally, the last one-dimensional integral, color-coded in green, is just the expectation of y. And we have this beautiful additivity property. The expected value of x plus y is the expectation of x plus the expectation of y. Now, this actually already suffices for our purposes, but there's a deeper additivity property just lurking under this analysis, and it would be a shame if we didn't pull it out. Okay? What if the variables were not independent? Well, in that case, we can't use the joint density as a product of densities. We'll have to go back to a joint density, p of x comma y. So let's write it down in terms of p of x comma y. Again, in the integrand, we have a sum x plus y, and the double integral separates into a sum of two integrals. And the change of variable theorem tells us that the first double integral on the right is just the expectation of x. The second double integral on the right is just the expectation of y. And so this property, this additive property of expectation, does not even demand independence. The expectation of a sum is a sum of expectations, even if the underlying variables are dependent, a fortiori if the variables are independent. But independence is going to be needed when we turn to variances, and we do this next. So let's start with our observation. If we start with two coordinate variables x and y which are independent, and we form their sum, we've discovered in particular that the expectation of a sum is a sum of expectations. What can we say about the variance of a sum? Let's promptly appeal to the change of variable theorem again. Identify f of xy with x plus y. The variance of x plus y is obtained by allowing x and y to vary over the entire coordinate plane, and at each point xy, look at the sum x plus y, compare it with the expectation of the sum, which we've discovered is the sum of expectations, square it, now we've got a squared discrepancy, weight it according to the joint density, which in our case now, because of independence, is a product of densities, and integrate out. There you go. Now, this looks complex, admittedly, but let's see if we can do a little algebraic massaging to simplify it. Inside the square brackets in the integrand, we find two terms, an x plus y and a sum of expectations. Let's group them by variable. So associate the expectation of the chance variable big X with the coordinate variable little x. Associate the expectation of the chance variable big Y with the coordinate variable little y. All right, and we can rearrange the sum, and now I'll put things inside round brackets, and we have inside the square brackets two terms in round brackets, and we're going to square the sum. Well, the square of a sum we know by the simplest application of the binomial theorem. A plus b squared is a squared plus 2ab plus b squared. Identify a with x minus the expectation of big X. Identify b with y minus the expectation of big Y. And now we've got three terms that the square of the term in the square brackets expands into. Integration again is additive. An integral of a sum of three terms is a sum of three integrals. Let's write each of these down one at a time. So first, we have an integral involving the term little a squared. Then we have an integral involving the term 2 times little a times little b. And then we have an integral involving the term b squared. And now we've expanded out into three terms. All right, so our expression is getting algebraically more cumbrous. Right? What is of the essence here is that we have three terms on the right. Let's give them names. uppercase A, B, and C respectively. And so our task now is to evaluate A, B, and C. So let's turn to this and see what we have. Let's start with A. A is the integral of a square. The integrand has devolved into a product of a function of x and a function of y, and therefore we iterate the integrals and write this down as a product of two integrals, 1 over x, 1 over y. Excellent. Now take a good hard look at the two terms on the right. Do they strike a chord? Well, they should. The first term is just the variance of x. The second term is the area under a density function. By normalization, it is 1. And therefore, the entire term A, the first term on the right, was just the variance of x. Let's promptly turn our attention to the term we call C. Again, we have an integral. The integrand devolves into a product of functions of x and y. We write it as two one-dimensional integrals. And now the analysis carries through in exactly the same way as for A, with the roles of x and y interchanged. And therefore, without further ado, we see that C is identified with the variance of y. All right, and that leaves the more cumbrous term in the middle, B. The factor 2 comes out of the integral as a constant. And again, the integrand is a product of a function of x and a function of y. The integrand separates. And so the double integral separates into a product of two one-dimensional integrals, 1 over x, 1 over y. Now, let's take a look at, say, the first of these integrals over x. A good hard look at the integrand shows the integrand is a difference. But integration is additive. The integral of a difference is a difference of integrals. And so we promptly write this down as the integral of x times p1, from which you subtract out the integral of an expectation times p1. But the expectation of x is a constant, say mu1. It can come out of the integral, and now we have a simple expression. The first of the integrals on the left is exactly the expectation of x. The second integral is unit by normalization, and therefore we have the difference of the expectation of x with itself, or 0. The first integral is 0, and for the same reason the second integral is 0. A product of 0 with 0 is 0, and so without further ado, that big complex term in the middle, b, vanishes quietly, like the snows of yesteryear. It disappears and does not trouble us any further. All right, let's put all of this together. What do we have? The variance of a sum has got three contributions, A, B, and C. A was the variance of x, B was 0, C was the variance of y. And so we've discovered that when the variables are independent, then the variance of the sum is a sum of the variances. Now, the additivity of expectation is at some level to be expected. After all, expectation is an average. Average is a sum. A limiting sum is an integral. And sums can be done in any order. And therefore, expectation should be additive, and in fact it is. The fact that the variables are dependent or not is irrelevant to the additivity of expectation. But for variance, we need something a bit stronger. Variance involves a square, and a square is intrinsically not linear. To recover linearity from a square, we are going to need more structure, and that structure is provided by independence. A curious listener might want to go back and ask, can I relax independence? Indeed you can, but it's clear that something along those lines is needed. I shall not dig into it any further at this point. We have more than enough for our purposes. Let's summarize our discoveries in two slogans. The first of the slogans for expectation. Expectation is additive with no qualifications. This turns out to be a fact of surpassing importance in the theory and the applications. In particular, expectation is certainly additive when the variables are independent. And the second slogan, variance is remarkably also additive, but with the proviso that the underlying variables are in fact independent. Now, with these two tendrils of additivity in hand, we are now equipped to launch into what Chebyshev's inequality says about a sum of independent variables. This comes next.